Hello everyone, thank you for accepting my paper. My name is Martin and today I will talk about driver fairness with monotone profits. I will start my presentation with a brief motivation. Then I will describe the contribution and the setting. After that, I will discuss how we might model fairness for drivers by presenting two possible ways of doing it. And in the end, I will conclude by summarizing my results. Let me start with the motivation. In the last years, more and more funds are being granted for future transport. One reason for it is that we want to make the related technologies trustworthy, safe, and transparent. However, even if we do that, Europe has recently announced that the transition to future transport may require involving the preferences of individuals. One research field we might look at for modeling preferences is computational social choice. Computational social choice is the field that is founded on the basis of aggregating preferences. This field intersects not only economy and game theory, but also computer science. Thus, my vision to build on trust and account for preferences in vehicle routing problems is to apply tools from computational social choice to such problems. I refer to the intersection as social vehicle routing problems, where preferences of drivers and customers play a central role in decision making. In this presentation, I will, however, focus just on the driver side of the problem. In my paper, I make several contributions, and I show these contributions on this slide. I present a novel model for assigning requests to drivers with vehicle feasibilities and driver monotone profits. I also formulate two new notions for driver fairness, namely envy freeness up to one request, or FEF1, and jealousy freeness up to one request, or FEQ1. I discuss how each of these notions can be achieved in isolation. I also suggest that they cannot always be achieved in combination, and that the corresponding decision problem belongs to the class of NP-hard decision problems. As a first step, I consider the model. In this model, I consider a set of requests, customer requests. Each request can have a different type. For example, a given request could require a visit to some location or a transport of people between two locations, say point A and point B. I also consider a set of vehicles in the model. Each vehicle can be feasible or not for every request. This is encoded by feasibility indicators. Additionally, each vehicle has some driver who gains some profit from servicing each given request. For this model, I consider feasible and complete assignments that give different bundles of requests to drivers, where each request with a feasible vehicle for it is serviced or assigned to a feasible vehicle. As I mentioned, I assume that the drivers have monotone profits. Basically, this means that servicing any additional request gives them the same or strictly greater profit. Three practical monotone profits are additive profits, sub-additive profits, and super-additive profits. Additivity is used by car sharing companies such as ShareNow and WeShare, where the profits are equal to the operating costs for servicing requests. Sub-additivity is used by companies such as IKEA and Hufna, where the profits for servicing bundles of requests are at most as the sum of the individual profits of the requests in these bundles. Super additivity is used by courier companies such as DHL and FedEx, where the profits are equal to the customer costs minus the operating costs for servicing requests. Again, as I mentioned, I also assume that the vehicles can be feasible or not for requests. Feasibility indicators are useful for modeling various practical situations. On this slide, I show one such situation and discuss more situations in the paper. Let us consider 3D package dimension constraints. The idea is that if a customer submits a new request for a package transportation, but the package cannot fit inside the trunk of a given vehicle, then we can assume that this vehicle is simply not feasible for this request. However, if the package can fit inside the trunk of some other vehicle, then we can assume that that other vehicle is feasible for this request, supposing that there are no other feasibility constraints that prevent that vehicle from servicing the request. Thus, we can set the feasibility indicators prior to the assignment decision making and then use these during this decision making. There are many real-world settings with monotone profits for drivers and feasibility constraints of their vehicles. On this slide, I show a number of such settings. Examples can be connected driving, car sharing, electric vehicles, healthcare vehicles, post vehicles, garbage vehicles, ride-sharing vehicles, relief vehicles, as well as the popular taxi vehicles. From this perspective, the model with driver monotone profits and feasibilities of their vehicles is quite practical. For such applications, I propose a new notion of fairness that is based on the idea that drivers may envy one another, but for such a fixed pair of drivers, this envy is eliminated whenever some request is hypothetically removed from their bundles. The notion of FEF1 is new because it accounts for the vehicle feasibilities, which is a feature that is absent in the traditional fair division models. I illustrate the notion in the following example, where the vehicles are feasible for all requests. The rate assignment in this example satisfies FEF1 because the first driver does not envy the second driver, and the second driver does not envy up to some request the first driver, which is confirmed by the inequalities below the red assignment. On the contrary, the blue assignment does not satisfy FEF1 because the first driver envies the second driver even after any request is hypothetically removed from the bundle of the second driver, which is confirmed by the inequalities below the blue assignment. This is not the only way how we might encode fairness in our setting. For this purpose, I also propose another new notion of jealousy freeness that is based on the idea of jealousy, not envy, and thus accounts for the objective or actual profits drivers have for the bundles of their colleagues. This notion is new because it accounts for vehicle feasibilities. For every 2 drivers, it requires that each one of them gets a profit for their own bundle of requests that is at least as much as the profit of any other driver up to some request for their bundle of requests. Similar to FEF1, there are instances where some assignments satisfy FEQ1 and some other assignments violate FEQ1. In the example from this slide, the red assignment is satisfying FEQ1 because by removing hypothetically the request of driver 2, we can eliminate the jealousy of driver 1. And the blue assignment is not satisfying FEQ1 because by removing hypothetically any individual request of driver 2, we cannot eliminate the jealousy of driver 1. These statements or claims are confirmed by the inequalities on this slide. I next compare assignments that satisfy FEF1 and FEQ1. One question that we may ask is about the level of fairness guaranteed by assignments that satisfy both of these properties. Unfortunately, there are instances where drivers care less about their profit envy, but more about their actual profits obtained at the end of the assignment or once the assignment is decided. I illustrate this in the next example with 2 drivers and vehicles feasible for 6M requests. In this example, we can observe that each FEF1 assignment gives a profit of 6M to the first driver and a profit of 12M to the second driver. However, this leads to profit inequality and hurts the well-being of the first driver. By comparison, FEQ1 assignments seem to improve the well-being of the drivers. Indeed, each FEQ1 assignment gives a profit of 8M to each driver, and thus minimizes the profit inequality to 0. As a result, however, we can conclude that assignments that satisfy both FEF1 and FEQ1 may not always exist. And in response, I investigated the related decision problem and proved that this decision problem belongs to the class of NP-hard decision problems. And my proof relies on a car production from the popular partition problem. Finally, I summarize my results in this paper. I presented 2 new fairness properties for driver fairness. These are FEF1 and FEQ1. I considered assignments that satisfy both of these properties. However, I established that some instances may not contain such assignments. Also, the related decision problem is NP-hard. In response, I considered satisfying these 2 properties or each of these 2 properties in isolation and proved that each of them can be achieved in polynomial time. For this purpose, I propose 2 algorithms in my paper. I refer you to it for more details about these algorithms. One of them relies on the idea of greedily maximizing the profit of drivers by revealing the requests in a certain order and giving each next request to the driver with the minimum profit. And the other one relies on a generalization of the popular psychoelimination envy algorithm. I will be happy to answer any questions that you might have. For this purpose, please use my email to drop me your thoughts or the questions that you might have. Thank you very much for your attention. And I am looking forward to meeting you all next year. Bye.